This man claims to have made one of the most remarkable breakthroughs in modern science. If he is right, then he has found a revolutionary new way to create a form of energy that could transform our world. It's called nuclear fusion.
It would mean that you could take water to fuel your car. That would ensure that 10 billion people over the next 10,000 years would not have to worry about producing energy.
But others accuse him of bad science and say his work threatens to bring back the ghost of one of science's most notorious episodes. It has blown up into one of the biggest scientific controversies of recent years. So tonight, Horizon will try to sort out the matter once and for all.
If you can't reproduce it, it's not science. Unless somebody else can reproduce those data, it'll just sort of wither away.
We have assembled a team of experts to conduct a unique experiment to test out these claims. If the result is positive, then this man will be on the way to a Nobel Prize. And the dream of a shortcut to a world with unlimited cheap energy could finally be within reach. But if it fails, one of the great dreams of science will surely die. The small town of Oak Ridge in Tennessee has witnessed some remarkable scientific discoveries. The first atom bombs were developed here. And since then, the Oak Ridge National Laboratory has been home to some of the US government's most secret nuclear research projects. Now, one of its scientists, Rusi Taleyarkhan, claims to have found something that could be an even bigger breakthrough for mankind. It's something that could potentially liberate millions of people trapped in poverty, save us from global warming, and transform the entire global economy.
If you raise the standard of living and have people be able to stand up and I guess be counted as human beings rather than be treated like dirt, the world would be a much better place for everybody. That would be the crowning glory of my life if I can make it happen.
But the claimed breakthrough has been condemned by many fellow scientists, and Rusi Taleyarkhan has faced a storm of criticism.
We had to stand firm on what we believed to be right. We knew that whatever data was obtained under the best of circumstances, with the best of intentions, and with whatever resources we had. And we believed the data.
What Rusi Taleyarkhan claims to have found is one of science's holiest grails: nuclear fusion. Nuclear fusion is nature's atomic power. At the core of stars like our sun, conditions are so hot and so extreme that atoms of hydrogen are forced together until they fuse. This natural nuclear reaction gives off massive amounts of heat, light, and energy. And many scientists are convinced that fusion could provide cheap energy for mankind forever. Because here on Earth, exactly the right fuel needed for fusion is locked inside water, the stuff that covers most of our planet. So every river, every lake, every ocean is a potential source of energy. Enough for everyone on the entire planet for millions of years. And to cap it all, nuclear fusion is clean. So it would spell an end to global warming. And unlike conventional nuclear power, there would be no nuclear waste. Not surprisingly, realizing this dream has been a goal of scientists for decades.
Fusion is one of the great quests of science. It's one of the great things that we would like to be able to do, like finding a cure for cancer. And we've known for 50, 60 years that there's this unbelievable amounts of energy that we could get if we could just figure out how to do it.
The key to releasing that energy was heat. Temperatures in the core of the sun are an unimaginable 10 million degrees. And recreating those conditions here on Earth has been one of the most difficult scientific endeavors of all time.
Nature does fusion. Nature does fusion in the center of the sun. But if you wanted to do it on Earth, you've got to recreate some kind of condition like the center of the sun. That's difficult.
For over 30 years, and at a cost of billions, mammoth fusion machines were built to try and achieve this goal. But the experiments always used up more energy than they ever produced.
10, 9.
Until in 1991, a team at this laboratory in Oxfordshire finally succeeded in producing enough energy to light up a few houses.
0.
But it lasted for just 1 second. A few years later, the same team were back at it. This time they produced enough energy to light up a small town for just 4 seconds. These bursts of energy were so short-lived that fusion scientists had to admit that the practical reality of a world with unlimited clean energy was still as far away as ever. But some scientists dreamt of an easier way to achieve nuclear fusion, a shortcut that would get mankind there quicker and cheaper. It was a dream that led to one of the most infamous scientific episodes of all time. On the 23rd of March 1989, Professor Martin Fleischmann made the most extraordinary claim. That he and a colleague, Stanley Pons, had discovered a simple way of doing fusion that didn't seem to cost the Earth. It was called cold fusion.
Well, the belief is that in order to create fusion, we have to slam two atoms together. Bang, we have to slam them together. And that has been the background to the attempts to create hot fusion. And what we were saying is, no. It may be that you can achieve fusion under much milder conditions.
What they had done seemed truly revolutionary. They had taken a test tube of the fuel for fusion, a type of hydrogen called deuterium, passed a simple electric current through it, and made the atoms fuse together. Nuclear fusion seemed to be happening almost effortlessly in a test tube, and it caused a sensation.
Two scientists are claiming a breakthrough in the production of energy by nuclear fusion, the same process that powers the sun.
It's been a dream of scientists for decades.
Dr. Bunce is an instant celebrity here.
Pons and Fleischmann became household names, as the idea of a cheap solution to all of mankind's energy problems caught the world's imagination. The rest of the scientific community quickly scrambled to catch up with Pons and Fleischmann and repeat what they had done.
Any scientific process ought to be able to be reproduced exactly.
Okay, we stop it there. Okay.
Like about 100 or maybe 200 other labs around the world, within a day, Princeton had set up some cold fusion experiments and everybody was trying to replicate the results.
Several hundred research teams around the world have been trying to prove the cold fusion
All
theory.
over the country have been rushing to replicate and test the results of an apparently successful nuclear fusion experiment.
Could be $100 million worth of research was done in a couple of weeks. Right? In terms of all the people's salaries that were paid for that time, all the people who are thinking about it, all the people who are trying to reproduce it, all the people who are spending their time carefully reading the paper and trying to understand it.
The world waited expectantly to see if the results could be reproduced. And to begin with, it seemed to go well.
Scientists at the University of Texas say they've repeated the experiment which claims to create nuclear fusion at room temperature.
109, okay. This morning's pictures from the Texas University showed energy and maybe history in the making. Minus 3.144.
The key was tiny particles called neutrons. Whenever fusion happens, neutrons are given off. So in theory, the presence of neutrons would prove that fusion had taken place. But there was a complication. On a small scale, neutron detection is notoriously difficult, because just tiny amounts of neutrons are produced, and these can easily be confused with something else. Naturally occurring background neutrons produced by the sun and found all around us here on Earth. And as neutron readings were double-checked, the picture began to change.
Britain's leading atomic scientists have poured cold water on the idea of cold fusion. British scientists who've carried out extensive tests say there's no evidence that it works.
This would have been a very significant discovery, and we're very sad that we've put all this effort in and failed to find anything.
Most groups across the globe eventually agreed that all they could find were background neutrons. But it had taken several months and cost millions of pounds to reach that conclusion. With no fusion neutrons, whatever was happening simply couldn't be fusion. And so what had started as the biggest scientific breakthrough in the world turned into a scientific embarrassment of epic proportions.
The two researchers who claim to have made the breakthrough have made no comment themselves.
There was a conflict situation within the newspapers, which escalated in the university. It was very bad.
Now, even Professor Fleischmann acknowledges he made a mistake.
It isn't fusion. It's not fusion in the narrow sense. It is not fusion. Charlatans, frauds, yes. Well, they'll say whatever they want to say.
Professor Fleischmann continued his work for a few years. But ever since March the 23rd, 1989, he has found it hard to get papers published in scientific journals.
So you just squeezed out. Extruded. Scientifically extruded. Well, never mind.
It seemed that the dream of a shortcut to nuclear fusion was dead. But then something happened to resurrect the dream. It began when physicist Seth Putterman heard about something that seemed more like magic than science. It was a way of turning sound into light. Seth Putterman was so intrigued by this idea that he set about trying to do it himself. It's a process called sonoluminescence.
The first time I saw sonoluminescence was in a darkened room. I was transfixed to look at this spherical flask of fluid. And you'd look into the center, and in the center see a glowing blue-purple light, which could be seen with the unaided eye. It looked like a star in the heavens.
Seth Putterman called it the star in a jar, a tiny spot of bright light contained in a flask of liquid. This star in a jar is made when a sound wave is passed through a small bubble inside a flask of liquid. And this sound wave makes the bubble do something remarkable. First it expands, then it collapses. And this collapse happens so violently that vapor molecules trapped inside the bubble slam together and heat up so much that the bubble gives off an incredible burst of heat and light, several thousand times a second, giving the appearance of a star. What made the phenomenon so exciting was the temperature of this star in a jar. On its surface alone, the light burns at tens of thousands of degrees. And Seth Putterman now contemplated a tantalizing possibility. Could the core of the collapsing bubble be even hotter? Hot enough for fusion.
One of the mysteries of sonoluminescence is to determine exactly how hot the interior of the bubble gets. In the sun, the interior can be millions of degrees, hot enough to cause fusion. And the thought crossed my mind that perhaps inside the collapsing bubble, the interior of the bubble might also get hot enough to cause fusion.
If so, this would be something truly amazing. By simply bombarding tiny bubbles with sound waves, temperatures of over 10 million degrees would be created. And nuclear fusion, the same reaction that powers the sun, would be happening almost effortlessly here on Earth. One organization realized just what was at stake: the US government. They immediately started pouring money into research to investigate whether sonoluminescence could finally be the shortcut to nuclear fusion that scientists had been dreaming of. And across the USA, several groups set to work trying to achieve this remarkable goal. One of those groups, based at Oak Ridge National Laboratory, was led by Rusi Taleyarkhan.
Late January 2001, late afternoon. Trying to look for signals. Now started pressing the button on our high-speed scope and just kept our fingers crossed and said, let's see what comes out. The very first time around, it started clicking. That was extremely exciting.
The clicking was the sound of a detector recording neutrons, the telltale sign of nuclear fusion. At the first attempt, it seemed that Rusi Taleyarkhan had done what nobody else had been able to do: make his star in a jar hot enough for nuclear fusion. The key to his triumph was a brilliant idea. In sonoluminescence, vapor molecules trapped inside the bubble smash together, heat up, and give off a flash of light. But Rusi Taleyarkhan realized that too many molecules might actually cushion the bubble's collapse, and so the reaction wouldn't be violent enough for fusion. So he started with smaller bubbles that contained fewer vapor molecules, which he thought would now be forced together with much more energy when the bubble collapsed, creating a much hotter core inside his star in a jar, a core that would finally be hot enough for fusion. And in January 2001, it worked, and he detected neutrons.
Elated is not the right word. Ecstatic may not be the right word either. I mean, it was difficult to sleep soundly at night that day onwards.
Rusi Taleyarkhan knew that his breakthrough would be big news. But he also knew that cold fusion had been big news before it was comprehensively discredited. So over the next few months, he checked his results and confirmed them with other tests. He measured the neutrons again and again, but the results were always the same. And only then was he convinced about the scale of his discovery.
Nuclear fusion is a major finding. Some people think that it may be worthy of a Nobel Prize. It would be nice if it were, but I don't keep dreaming about it. If it happens, so be it.
And so the dream of a shortcut to nuclear fusion and the prospect of unlimited clean energy was alive again. But that was just the beginning of the story. For such a huge breakthrough to be scientifically accepted, the results first had to be published. Rusi Taleyarkhan aimed high and sent his paper to one of the most prestigious scientific journals in the world, Science magazine. Its editor, Don Kennedy, remembered just what had happened with cold fusion.
With the overhang of cold fusion, one would naturally be a little hesitant about a fusion claim that looks improbable. But you shouldn't ignore something because it's scary. I think the experiments were very well done. I found them convincing. And so, although we recognized that this was going to be controversial, we really thought it was a very interesting finding.
Science magazine sought out the opinions of other experts in the field. And although their comments were not all favorable, Don Kennedy decided that on balance, this remarkable paper was good enough to print.
We felt really comfortable about going on with the paper, comfortable in the sense that it was solid work from a very good laboratory by good people, and it would have to then endure the test.
So on the 8th of March 2002, Rusi Taleyarkhan received the endorsement of America's most prestigious scientific journal, and his fusion results were published in Science magazine. And immediately ran into a storm of criticism.
The figures of substance
That serious flaws had somehow been overlooked.
is that we're dealing with things in the article didn't seem quite right.
Confused. We found this paper unready for publication.
Less than.
Ultimately, many scientists felt the paper should never have been published at all.
Claims require extraordinary proof.
Fusion research is a heavily contested field, both because there are reputations to be made and because the amount of federal dollars spent on it is quite large, and people want their share of that research support. So don't ever expect this to be a peaceful domain in science. It's not going to be.
The criticism focused on one crucial issue, the same issue that cold fusion had foundered on: neutron detection. The best way to check if fusion was happening was to detect neutrons, the tiny particles that are given off when atoms fuse together. But there was one major complicating factor. Rusi Taleyarkhan was also using neutrons in his experiment. The small bubbles that led to his breakthrough were created with a device called a pulse neutron generator, which fired out over 1 million neutrons a second. And sorting out these background neutrons from any created by a small fusion experiment, although possible, was no easy task. Some scientists suspected that Rusi Taleyarkhan's fusion neutrons could in fact be coming from his own neutron generator. Bouncing around the room, and then entering the neutron detector, where they were mistaken for evidence of fusion. Rusi Taleyarkhan had an answer. He had conducted several control experiments to rule out the influence of background neutrons. But even in Oak Ridge, there was a conflict over his work. The management of the laboratory was sufficiently concerned about Rusi Taleyarkhan's fusion claim to ask someone else to double-check it.
And now we'll count for another 2 minutes and see how many we got.
They called in Mike Saltmarsh, an expert neutron hunter with over 30 years' experience of neutron detection and fusion.
42,043 neutrons. 42884. The reason I was asked to look at it is actually I hate to sound immodest, but I'm rather a good experimental physicist, and I do bring a background in neutron detection.
Mike Saltmarsh's task was to work out whether the neutrons detected could indeed be from fusion or were simply background neutrons from the neutron generator.
There is always a background, some of it due to natural background radiation. In the case of this experiment, there was an additional enormous background from the neutron generator itself, which was producing 1 million neutrons a second that were going all over the place. And consequently, any neutron detector has to be able to sort out whether the neutrons it's seeing are from that or from something else.
The way to do it was to run the experiment again in Rusi Taleyarkhan's laboratory, where Mike Saltmarsh could measure the neutron background, take it into account, and then concentrate on finding fusion neutrons over and above that. So he took a neutron detector, set it up, and after extensive testing, he found no evidence of fusion.
If there had been fusion going on at the sort of rate that Taleyarkhan's paper was claiming, we should have seen an enormous increase in the neutron detection. And we didn't.
Instead, Mike Saltmarsh thought that any fusion finding could be explained by the background neutrons from the pulse neutron generator. So he wrote up his report. And a couple of months after Rusi Taleyarkhan's paper, this was also published. It was a damning conclusion. Rusi Taleyarkhan and his team disputed Mike Saltmarsh's conclusion. But for the next 2 years, there was a steady stream of criticism.
There's been many a day that I come home dejected, desperate, but not until somebody really goes through trials and tribulations like of that type, being called all kinds of things, nasty things, it shakes your self-confidence and your value as a human being sometimes.
Eventually, he decided to try again. So he designed a new experiment with better neutron detection. And after months of checking and confirming, the results were ready. This time, the neutron signal was even stronger. And he was convinced it simply had to be from fusion.
Now there is very, very, very little or absolutely no chance that these neutrons could be confused as having come from the pulse neutron generator.
So he sent these results to Physical Review E, a highly respected journal. And after an extraordinarily thorough review, they were accepted for publication.
Look, everything we've gone through, all the trials and tribulations and the gut-wrenching feelings that you could be wrong and you might be making a fool of yourself on the world stage, you feel like, I guess you've been, what's the right word, vindicated.
But despite this second publication, many skeptics still weren't convinced. They believed that there was one vital measurement that still hadn't been made. It was a measurement that could finally prove once and for all whether Rusi Taleyarkhan's neutrons really were from fusion. It was all to do with timing. If fusion was taking place, neutrons should be recorded at the very moment the flash of light was given off. The flash of light would be recorded like this, and the neutron would be recorded at exactly the same time like this. But there was a complication. Sonoluminescence light flashes are incredibly fast. Each flash lasts just a nanosecond, 1/1000th of a second. And if fusion was happening, then any fusion neutrons should be produced at exactly the same billionth of a second. And should be recorded like this, together. But Rusi Taleyarkhan's instruments could not measure with nanosecond accuracy. They measured over a much longer timescale, which meant that stray background neutrons recorded sometime after the flash of light. Here or here, or here, could still be mistaken for signs of fusion. So to convince the skeptics that fusion really was happening, the burst of neutrons had to be recorded in the same billionth of a second. If not, they wouldn't be convinced that it really was fusion.
Unfortunately, this particular measurement, which is within the capability of modern technology, has not been presented in either the first paper which appeared in Science magazine or in a follow-up paper.
Rusi Taleyarkhan believes that he has repeatedly detected neutrons at the same time as flashes of light, and that he has already proven his claim beyond a doubt.
My lab has been audited. My instruments have been audited, my books have been audited. The data speak for themselves. The data have to speak for themselves, and it's difficult to, I mean, how can I answer that I know absolutely 100% sure that it is what I think it is? I just have to look at the data, and the data have been looked at very carefully. In the history of publications, I probably will not be able to find one that has gone through this level of scrutiny. If you do, let me know.
If he's right, a great discovery has already been made. But if he's wrong, his reputation could be severely damaged. The dream of a shortcut to nuclear fusion hangs in the balance. So tonight, on Horizon, we've decided to try to resolve this extraordinary dispute once and for all. We're going to try to make fusion ourselves, the same way Rusi Taleyarkhan says he does it. It'll be the first comprehensive and independent attempt to repeat Rusi Taleyarkhan's fusion results. A sacred scientific principle is at stake. The principle of reproducibility.
Nothing is too wonderful to be true that it can't be reproduced in another experiment. And this is what distinguishes science from religion.
If Rusi Taleyarkhan's results cannot be reproduced independently, the claim could suffer the fate of cold fusion.
Well, professionally, it would be difficult to live with. But on a personal level, I don't care.
If we do get fusion, one of the holy grails of science may finally come within reach, and the Nobel Prize would surely follow. For Rusi Taleyarkhan, if not for Horizon. So we've assembled the best experts to try and sort it out. Seth Putterman, the man who first realized the potential of sonoluminescence, will run the experiment. Whilst back in the UK, a team of leading experts will scrutinize the experiment and analyze the results. Professor Tim Mason from Coventry University, an expert in sonoluminescence. Dr. Nigel Hawkes, a world-renowned expert on neutron detectors from the National Physical Laboratory. Dr. Mike Laughlin from the UK Atomic Energy Authority, an expert fusion neutron hunter brought in to check the neutron data. And Professor Kathy Sykes to help cut through the technical jargon. We even invited Rusi Taleyarkhan to come to the laboratory and check Seth Putterman's equipment. But he declined our invitation on the basis that in the small and competitive world of fusion science, he did not feel comfortable with Seth Putterman's group.
I would help out anybody who I felt comfortable with. I would, but I've got to be comfortable with that particular group.
Why is that? Because it's not just science.
I will not answer that question right now.
So without Rusi Taleyarkhan's input to the experiment, our team had to follow his recipe for fusion from the published papers. In early October 2004, Seth Putterman and his team went to work.
In addition to how carefully it's degassed?
That's actually the biggest key that
First, they set up the experiment.
we have to get rid of the dirt, or else it's just going to cavitate everywhere. So we have to make sure we filter it to get rid of it.
They started with a liquid in which the bubble would be created, a liquid called acetone, to which deuterium, the type of hydrogen needed for fusion, was added.
And so we have to make sure we filter it extra well.
It was treated to remove any excess gas that might prevent the bubbles getting hot.
Now what comes across here? I don't understand. That this comes to here and then out somewhere?
And that goes down to the trap there. And that's what
Then came the neutron generator, the vital piece of equipment needed to make the bubbles. Rusi Taleyarkhan used 2 different types of neutron generator and got fusion both times. So our team made sure their generator matched one of those. Then the flask in which the bubbles would be created was installed.
The cell looks a little bit foggy.
Still cold from the refrigerator.
Rusi Taleyarkhan said that the design of the flask was important. It had to survive being bombarded with sound waves. So our team ensured that their flask was up to the same job. Finally, Seth Putterman made one major improvement, and a neutron detection system much more accurate than that used by Rusi Taleyarkhan was installed. Using this, Seth Putterman would be able to record any fusion neutrons at the exact moment, the very same nanosecond as the flash of light. If there were any there at all.
So just to be clear, that we can really compare the 2 experiments.
Because of the specialized nature of the equipment, not everything could be identical. So we asked our UK experts to scrutinize whether minor differences in equipment were likely to prevent fusion.
There is one classic difference, which is the source of the neutron. The energies are different. The source produces lower energy neutrons.
Now, would that matter?
Not according to Taleyarkhan, because in his first paper he said he got this effect.
The neutron generator got a clean bill of health.
Is the sound wave that he's applied just the same?
Slightly different frequency?
Yeah.
Minor. I don't think minor
You don't think that would matter? No. Okay, so...
And so, our experts were convinced that the recipe for fusion laid out in Rusi Taleyarkhan's published papers had been followed as closely as possible. Confident that he could reproduce Rusi Taleyarkhan's vital scientific conditions, Seth Putterman went to work.
So have we got the deuterated acetone in the cell?
Everything degassed just well.
So we're cooling down now in order to get to 0 degrees?
Yeah, we're getting there. We're at 7.5 degrees.
And Brian put the source in.
Yeah, put the source in.
Ready to roll. Let's get the data. Let's see what we can find.
Yeah.
On October the 7th, 2004, the test chamber was sealed. The sound wave started, and the experiment was underway. In 2 6-hour runs, spread over 3 days, sound waves bombarded bubbles inside the flask. And the neutron detector did its work, searching for neutrons in the same nanosecond as flashes of light. To give the experiment the best chance of success, Data from 4,000 bubbles was painstakingly recorded.
Looks like a really good resonance. It's good. That's really good.
And when the experiment finished, to ensure fair play, all the data was sent off to the UK to be thoroughly checked and analysed.
So let's try to summarise the different results that we got from...
A few weeks later, our team came together to discuss the
We'd
results.
expect them both to see were the bubbles. Are the bubbles reasonably similar, or can we say there are a few differences?
They're the same,
They're the same,
as far as we can tell.
as far as we can tell, okay? And then we've got the sonoluminescence. So these are the flashes of light. We know that Rusi saw them. How about Seth? Did he get that too?
Yes, he saw it as well.
So there's a load of energy being produced. We know
It was clear that our experiment successfully produced bubbles that gave off flashes of light.
When you get the flash of light, that's exactly the same time that you expect the neutron to be produced.
Yes, if the neutron is coming from fusion, you'd expect to see it at the same time as the flash of light.
But then it came down to the biggest question of all. Just how many neutrons did Seth Putterman record in his neutron detectors in the exact same billionth of a second as flashes of light?
And how about Seth?
None above the background.
None.
None at all.
Our experiment failed to find any evidence of fusion. We put this conclusion to Rusi Taleyarkhan. He said that it had taken him several years to perfect the exact conditions necessary for fusion, and that because our experiment was not an identical copy of his, any one of several differences might have affected the outcome. Nevertheless, we followed his fusion recipe as closely as possible, on the principle that if the key scientific conditions are reproduced, the results should be too. But we found nothing. It is possible that other scientists may succeed in reproducing Rusi Taleyarkhan's results. But for now, all we can say is that the dream of a shortcut to unlimited, clean energy forever must remain just that. A dream.
Next week, one of the most controversial subjects in science, designer babies. Could we one day create a world where every child is genetically perfect? And if we could, would it be right? Horizon cuts through the hype to get at the truth. What is a designer baby, and can we really create one?